Our next speaker is Florent.
Right. Good afternoon, everybody. Good morning in New York. So my name is Florent Leclerc, and I'm based at IAP. This is a flash talk about a specific project about dealing with systematic effects and making the link with the issue of model misspecification in statistics. So let me first explain why these two are related. So model misspecification is a long-standing problem in Bayesian inference. When the model differs from the actual data generating process, you typically have bias posterior or you are overly concentrated. And this is particularly critical for cosmological data analysis in the presence of systematic effects. This is true in particular in cosmology, where sometimes we are unable to formulate any model that fits the data in some regimes. That is true at large scales, for instance, in the presence of observational effects. Also at small scales sometimes when you talk about baryonic physics and these hydro simulations giving different predictions. Now, with an explicit field level likelihood, and we've heard a few talks about that previously, it's possible to have a machine-aided report of unknown systematic effects. And this is what was implemented in the Borg code, for instance, where there's this robust likelihood which automatically reports unknown contaminations in the data. That's one foreground here in the SDSS3 data, which was discovered by Borg, and which reports this unknown contamination and marginalizes it over it. So now, how do we do when there's no explicit field level likelihood, but we're talking about implicit inference problems? We want here to propose a two-step framework, where we have this kind of Bayesian hierarchical model here on the left, which includes in particular our latent function, which is the initial matter power spectrum, which comes from your Boltzmann solver. You have a complex observational process giving your galaxy catalog, and at the bottom, compressed summary statistics. So what we propose is to do in two steps. There's first the SELFI algorithm, which allows you to go from galaxy catalog to the latent function, meaning in physical terms, you get a reconstruction of the initial matter power spectrum from black box model. You can then utilize the initial matter power spectrum to check for systematics, and this is in particular what my PhD student Tristan Hollinger is looking at, and he is characterizing all of the systematic effects that you can have in this reconstruction of the initial matter power spectrum. And the second step is then to do implicit inference, which is to go from the bottom, compressed summary statistics, to cosmological nuisance parameters. As a bonus, the simulations that you have for step 1 can be recycled to give you a free score compressor for step 2, which is typically required for implicit inference. Now, we are typically talking about very expensive simulations with n-body code, etc. So we can typically afford about 10,000 evaluations. So emulation of this is possible, and it's one of the major topics of this conference. But here I wanted to quickly flash another idea, which is to use Bayesian optimization to place the simulations in parameter space. Use an acquisition function, which places the expensive simulation in parameter space, allowing you to massively reduce the number of evaluations as compared to MC to get basically the same posterior. And in fact, the optimal acquisition function for implicit inference can itself be derived. It's called the expected integrated variance. This is what it looks like at play for supernovae data. And I'll let you have a look at the papers if you're interested in checking more details. Here were the references. Thank you for listening.
Thanks, Florent.